Hurricanes, floods, and tornadoes dominate our disaster coverage. Yet extreme heat kills more people in the United States each year than all three of those forces combined. To survive a severe spike in temperature, the human body relies almost entirely on a highly efficient biological mechanism, the evaporation of sweat. This chart tracks heat and humidity, pinpointing the wet bulb limit. At 31 or 32 degrees Celsius and 100% humidity, sweat stops evaporating. The body cannot shed heat. Core temperatures spike. Within 6 to 8 hours, adults experience heat exhaustion, stroke, and eventual death. That rigid mathematical limit is even lower for specific populations. Infants lack fully developed sweat reflexes, leaving them unable to throw off excess heat, while older adults process thermal stress through a slowing metabolic rate. As global average temperatures rise, these extreme conditions are starting earlier in the year and lasting much longer. We are rapidly outpacing our own physiological evolution, reaching a point where heat transitions from a seasonal discomfort into a hard biological stop. To bypass these physical limits, we are attempting to engineer our way out of the crisis, starting at the personal level. Low-tech defenses include aggressive hydration and the use of electric fans. However, in super high, extremely dry heat, fans can actually accelerate danger for the elderly by evaporating moisture too quickly and preventing the normal sweating process necessary to cool the core. For a higher-tech approach, researchers are looking toward advanced wearables. Technologies like the liquid cooling garment worn inside this NASA spacesuit use thermoelectric coolers and circulating fluid to artificially regulate human body temperatures. We are also attempting to engineer survival on a municipal scale. This cross-section shows the mechanics of the urban heat island effect, where dark pavement and buildings absorb massive amounts of solar radiation. Looking at the exact same city block at night, trapped thermal energy radiates back out. This prevents the nighttime cooling necessary for the body to recover, allowing deadly thermal stress to accumulate. Some cities are actively intervening to break this cycle. Medellin, Colombia planted a massive network of lush green corridors along its roads and sidewalks. In just 3 years, that dense tree canopy brought the city's overall temperature down by more than 2 degrees Celsius. Other regions are installing physical infrastructure. Seville, Spain became the first city to name and rank heat waves the way we do hurricanes. It deploys extensive canopy systems to shield pedestrians from direct solar radiation. These engineering feats prove that adaptation is possible, but they remain highly localized solutions. The vast majority of the global population is currently living without these structural protections. There is a severe equity gap in our response to extreme heat. High-tech chill suits and shaded European plazas stand in stark contrast to the daily reality of outdoor labor. Workers who maintain our global infrastructure and agricultural systems must operate directly in the sun, relying entirely on manual effort to keep society functioning. The heaviest burden of this escalating heat falls on populations in the global south. Regions across Africa, Indochina, and South America are experiencing severe, prolonged heat waves without the resources to build sweeping cooling networks. Even within wealthy nations, protections are scarce and sometimes actively dismantled. In the United States, states like Texas and Florida have passed laws explicitly prohibiting local governments from mandating heat protections and water breaks for workers. When access to cooling is dictated by wealth and zip code, survival becomes a luxury. The climate crisis forces us to confront an environmental injustice where the populations with the least political power endure the highest mortality. The ultimate limitation of our engineering hierarchy is scale. We can air condition a building, and we can shade a city street, but we cannot air condition a collapsing planetary ecosystem. While we focus on the land, 90% of the excess heat from climate change is actually absorbed by the oceans. That massive thermal shift triggers marine heat waves that devastate aquatic life, collapsing food webs and pushing species like the emperor penguin toward extinction as their essential fast ice melts away. On land, rising temperatures are destroying the global snowpacks that traditionally function as massive, slow-release water systems. Throughout the Himalayas, early snowpack melting threatens river levels across the entire region. This jeopardizes the direct water supply and agricultural capacity for over 1.2 billion people. To combat these severe regional droughts, nations are forced into desperate geoengineering workarounds. China, for instance, is currently constructing extensive south-to-north water diversion canals to keep its dry northern cities functional. As power grids struggle to keep up with the rising demand for air conditioning, we face the very real prospect of comfort rationing, a future where authorities cap personal electricity usage to prevent grid collapse and maintain wider community survival. 8 billion people cannot individually life-hack their way out of a boiling climate. Achieving true climate equity requires a dual approach, building immediate, aggressive community resilience to protect the vulnerable right now, alongside rapid global emissions cuts to actually cool the planet.